Alright, this is going to be a quick video on how to make a Bohr-Rutherford diagram. Here I'm just chose the element fluorine and looked up on the periodic table to see that fluorine has an atomic number of 9 and an atomic mass of 19. And for this first video, we're just going to talk about how to do this for assuming that fluorine is neutral, and we'll deal with anything like ions later. So here, that's the atomic number and the atomic mass. And in a previous video, I explained that the atomic mass is the total of all the mass of particles in the atom. So this is equal to the number of protons and neutrons. And this, the atomic number, is the number of protons in the atom. So if I want the number of neutrons, then the way I can do that is I take the atomic mass minus the atomic number. So 19 minus 9, which gets me a value of 10. Note here that this 19 on the periodic table might not be exactly 19. Like it might be 19.01 or 18.9 or something like that. But because the number of neutrons can't be a decimal place like that, we always round that number to some normal number or to some integer when we're doing this, so that we don't say we have like 10.1 neutrons. We never do that, okay? So we always round it to a whole number. So we get whole numbers of protons and neutrons. Okay, with that in hand, we've got the number of protons and the number of neutrons. Protons are 9, neutrons are 10. So for our Bohr model, we put those two things in the middle. Protons 9, neutrons 10, sitting in the middle. And then I have to put in my electrons. Since I said that this atom was neutral, and we know that protons are positive, and electrons are negative, then if it's going to be neutral, the number of protons is going to be equal to the number of electrons. And as a result, the two will cancel each other out and give us no charge. So here, my number of electrons is going to be equal to my number of protons, which is 9. So I create a shell or an orbit around my nucleus. This nucleus is way, way, way too big, but I have to write p equals 9 and n equals 10, so I can't make it anywhere near small enough. It should be way smaller. Anyway, my first shell can hold 2 electrons, so I just put them on as little e's. And you'll see I put one at the top and one at the bottom. That's just sort of a reminder to myself that these electrons will repel each other, try and stay away from each other. And then I'm going to add another shell. Since I've used up that whole shell, I can only put 2 in it. And my subsequent shells will each hold 8. For the purposes of grade 9, that is a good enough rule. We'll just go 2, 8, 8, 8, 8. And later when we take higher level chemistry classes, we'll learn that there's a little bit more sophistication to the number of these electrons that can go in each row, but 288 is great for now. Anyway, I have 9 total and I've used 2, so that means I have 7 left to go. So I'm going to put 1 up here, 1 up here, 1 down here, and 1 over here, so that gets me 4. And you'll notice that I'm not pairing them until I have to, so I'm showing that they like to repel or they like to be away from each other. And then I'm going to add 1 more here, 1 more here, and 1 more here, and I get 2, 4, 6, 7, 8, 9. That matches the 9 that I'm trying to have, and so that's the Bohr-Rutherford model for fluorine. I'm going to label him nicely up here, and that's that. We'll do 1 more here. No particular reason, but we'll look at magnesium. Oh, maybe this will help too, because magnesium's atomic mass is 24.3. So recall earlier that I said when we go for atomic number, by definition, that tells us the number of protons. So in this case, that's 12. And when I go for atomic mass, I use this 24.3, but I'm going to round that to 24 when I'm actually looking for the number of neutrons, because I don't want 0.3 of a neutron. That doesn't make any sense. Neutrons are, there's a neutron or there isn't. There's 1, 2, 3, not 1.3. So I just round that to avoid that error. Now, my number of neutrons is equal to my atomic mass minus my atomic number. So in this case, 24, the rounded value to avoid decimal places, minus 12, meaning I have 12 neutrons. And once again, in this video, we're keeping it simple. We're making them neutral, which means that there's no charge, which means since protons are positive and electrons are negative, they have to cancel each other out. So the protons equals the electrons, and since we already knew that was 12, we have 12 electrons. Again, the protons and neutrons are located in the nucleus of the atom. And again, remember, this model is a bit of a representation. The nucleus is way too large. But again, that's fine. It's just, remember, it's a bit of a misrepresentation. In our first electron shell, here, we can hold 2 electrons, then we can hold 8, and then we can start a new shell and hold 8. So our first little shell can hold 1 at the top and 1 at the bottom, and that's that. And my next shell can hold 1, 2, 3, 4, 5, 6, 7, 8. So now I have a total of 2 plus 8. I'm up to 10, which means I have 2 left over for the next shell. And I'll put 1 up here and I'll put 1 down here to show that they're repelling. I'll keep them out of the same shell or away from each other. And that's that. That's the Bohr-Rutherford model for magnesium. So I will just label him nicely, magnesium. And that's how you make a Bohr-Rutherford diagram. I'm going to do another video where I talk about what you do when you have ions. So again, that'll be a little bit of an extension, but something that you can look at if you are finding this sort of straightforward.